because the digestion of fat is quite a complicated story, which we'll talk about probably tomorrow. Now, let's just talk about hiatus hernia. It's a common problem with people. Anytime an internal body part pushes into an area where it doesn't belong, it's called a hernia. Now, the hiatus is an opening in the diaphragm, the muscular wall separating the chest cavity from the abdomen. Now, normally, the esophagus or the food pipe goes through this opening and attaches to the stomach. In a hiatal hernia, also called hiatus hernia, the stomach bulges up into the chest through that opening. So it looks like this. Here's the stomach bulging up into the chest. It shouldn't do that. That's a hiatus hernia. Now, you get bile reflux. Even if the sphincter, as we grow older, our sphincters begin to weaken because they're just muscle. You get heartburn. You get terrible feelings in your chest. You get this disease, gastroesophageal reflux disease. It's called GERD. Gastroenterologists call it GERD for short. And it's a very common problem. Sometimes you think you're having chest pains, which resemble a heart attack. And the more serious problem is you can get, over a long period, you can get Barrett's esophagus. And that's not a nice condition to have. The esophageal lining changes to tissue that resembles the lining of the intestine. Barrett's esophagus can become cancerous. Okay? So it's quite a serious condition. So if you have heartburn regularly, do something about it. Take some antacids, go and see your gastroenterologist. Now, esophageal cancer, the incidence in South Africa is highest on the continent, right? It's also very high in China, but in Africa, South Africa is the highest. And in South Africa, in the Eastern Cape, the former Transkei region, it's the highest in this country. Now, it's associated with smoking and alcohol consumption, right? So that's scientifically shown. But there's anecdotal evidence that it is also caused by aflatoxins, the Aspergillus molds, and fumonisins, which are molds, right? Fungi. Now, there is a habit especially amongst the Xhosas, a cultural habit, when fermented beer, or mkomboti as they call it, is drunk out of a tin or an iron pot, the iron is leached into the beer, causing an iron overload, and they think that could be a causative factor for esophageal cancer. But that idea is still anecdotal. It's very difficult to quantitate. Now, these aflatoxins I heard about as a student, and I was particularly interested in them because they were associated with liver cancers. It's found largely in the covering of nuts. So it's a toxic fungal metabolite produced by Aspergillus, and it causes chronic toxicity in humans. They may be present in a whole lot of foods, but I've put in bold here peanuts because that's what I first heard about from Mozambique onwards, that people eat the peanut without shedding the outside, and that contains aflatoxin. Milk, cheese, and other dairy products also has it. The highest levels are found in commodities from warmer regions of the world where there is a great deal of climatic variation. And aflatoxin B1 specifically is associated with an increased risk of developing liver cancer, an impaired immune system, and malnutrition. So while I was here, I thought I'll drop a big name or two to make myself feel better. This is Philip Gould. He was the former aide to Tony Blair. Now, I first came across Philip Gould's story. I was traveling on a train once from Cambridge to London, and whenever I'm in England, I try and buy as many newspapers a day because I love the British newspapers. So on this particular day, I remember for some reason, or for no particular reason, I chose the Times, which I don't actually read. I read The Guardian, I read The Independent, and if I want some gossip, I read some of the other newspapers. So I picked up the Times, and there was the serialized version of a story of Philip Gould, Tony Blair's advisor. He's the architect of New Labour, and he was a very close aide to Tony Blair. Now, he developed esophageal cancer at that time. Now, in May 2008, after 3 months of chemotherapy, throat and stomach surgery, he did something strange. He decided not to be treated in the UK anymore. He didn't want to be treated in the NHS, so he flew over to New York to Dr. Murray Brennan at the Memorial Sloan Kettering Cancer Center in New York. Right? Now, unfortunately for him, things went horribly wrong. So even world-class surgeons or world-class doctors can make mistakes. And his prognosis became very poor. He came back to England, and some of his friends in government said to him, Philip, why did you travel all the way to New York when we have the best esophageal cancer man right here in the NHS in this country? And that man was Professor Mike Griffin at Newcastle's Royal Victoria Infirmary. And why I felt very important is that I was attached to that university and teaching hospital while I was there. And Mike Griffin had the largest esophageal unit in Europe. Now, so Michael Griffin, professor of GI surgery, has been performing complex surgery for more than 2 decades. He's had excellent results. He has saved countless lives, and he's played a pivotal role in the creation of the Northern Esophageogastric Unit at Newcastle's RVI. Okay? Now, what he had to do, apparently, and this is now, I remember reading in the Times, was that he gave Gould a leash on life. So Gould, he was able to undo some of the damage that was done. He probably did something which gave Gould an extended life, so that Gould could reconcile with his children, could spend more time with them, and could write a book which became a Sunday Times bestseller, When I Die. And this is the book that was serialized in the Times. And it's one man's extraordinarily powerful and ultimately inspiring account of how he came to terms with the most devastating news of all. But he said something strange. He said, I'm enjoying my death. It's the most fulfilling time of my life. Now, you know, I don't want to sound morbid, but there's a New York Times bestseller that's going around at the moment of an Indian-born neurosurgeon who's had an amazing career at Stanford and Yale and has had degrees in English from Stanford, from Cambridge University, where he did a master's in philosophy, then came back to the United States, did medicine at Yale, and became a top neurosurgeon who was very much in demand, and at 37 years old, and he got diagnosed with a lung tumor. And then he also wrote a book, and it's an extremely engaging story. It's called When Breath Becomes Air, and his name is Paul Kalanithi. And he's just died recently, and his book hasn't come to South Africa yet, but we've picked it up on the Kindle. My daughter actually referred it to me. So, what happened to me? Why am I feeling so great? Mike Griffin actually floated into my office one day, here in Cape Town. And he said, hello, I hear you're in Newcastle and you're a mucus man. I'm Mike Griffin, and I got the shock of my life. I said, are you the Mike Griffin? And he says, what does that mean? And we spent the morning together, and it was a very interesting morning. He told me about his life. He was in school with Tony Blair, something that he's not proud of, but I'm not going to go any further there. Okay. Let's go back to the stomach, to more mundane matters. So, the stomach as an organ of social adjustment, it says here, genius, doubtless, like an army travels on its stomach, but what a stomach. The reason that we stand in awe of the stomach is that this organ, more than any other of the viscera, controls our social adjustment. Okay, you can't deny that. Now this article is from one of the most conservative Muslim newspapers in this country. If you read this newspaper, everything you do is wrong. You want to go to heaven, you've got to follow this one particular path. But this man wrote this little piece, and he spoke about advice from the Prophet. And he said, those who are unable to adopt the austere method of eating exhorted by the Prophet should at least not overeat. As soon as the stomach is about to be filled, one should exercise restraint and stop eating. And then he got a bit carried away. He's not a medical man. He said, your body's worst enemy is your stomach. Suffering from asthma? It's your stomach. Are you losing your memory? It's your stomach. That I can agree with. Are your arteries diseased? It's your stomach. So I think he should stick to his religion. Now, what I'm particularly interested in is that once the food enters the stomach, it actually enters hell. And these sphincters here close. This is the lower esophageal sphincter, and this is the pyloric sphincter. So the food comes in here. And as I said to you the other day, this is really hell. Your acid is so potent that a drop of it could burn a hand through the skin. And yet you don't even know, you're not even aware of what's going on while your food is being digested. And there's got to be a reason for that. What is so special about the stomach? Because this acid has already been secreted before the food arrived. The minute you get the aroma of the food, or you're hungry and you think of food, the brain sends a message to the stomach and says, get ready, food is coming. This guy is hungry. And so this potent acid enters the lumen of the stomach, and it converts an inactive enzyme, pepsinogen, to be active. Now, if you're fasting, you're not eating, you're hungry, but you walk past this particular shop and you've had this aroma wafting across, and you secrete acid and it activates pepsin. That pepsin, if it doesn't see any food to act on and break down, any food protein, it's going to turn against the walls of your stomach. So that's pretty dangerous. So don't fast too much, is my advice to you. Okay, now there's other aspects that we're going to talk about. If you look here, that's the story of my career and my life. The layer of mucus that actually lines the epithelium of the stomach. Okay, so we'll come across. So here's a better view, and you can see the inside of the stomach wall. It looks like rugae. So a lot of people think it looks like the brain, but it's very folded, it's compact, and it covers quite a large surface area. Now, if you open the stomach, this is what it looks like. Okay? Now, the cells. Now, as I said to you, we're all made of cells, and cells make tissue. And that tissue need not have cells that are identical. So in the stomach, we have parietal cells, which produce acid. We have mucus-producing cells. We have G cells, which are endocrine cells, which secrete a hormone called gastrin. We have histamine-producing cells, and that's very important because I'm coming to treatment of ulcers just now. And we have the chief or the peptic cell, and that's what it looks like. If you get very close and look under a microscope, you'll see that the surface of the stomach has this epithelium, and it's all a part of a duct. And in that one duct, you can get a variety of these cells, as I've described to you here. Okay, so look at that one gland. So it starts at the surface and it goes down, and look at the variety of the types of cells. That's called the isthmus on the neck, and then the neck of the gland, and then the base. And along the way, if you walked down here, you'd meet a whole lot of different cells, okay? And all have different functions, and they all secrete different things. It's absolutely fascinating. And so if you look at it now, so those are your glands, and then you secrete from these cells, you secrete acid, and from another cell, the acid would go to pepsinogen, which is inactive. This is absolutely fascinating, that when you actually make an enzyme, it is in its inactive form. And that's great, because if you don't have any food around, you don't want the active enzyme to turn against the very own wall of your stomach. So once you activate pepsin, then you get autocatalysis. That means the pepsin then goes back to the inactive form and activates the inactive form automatically. So pepsinogen is converted to pepsin, and then the pepsin looks for the protein that you've eaten and starts nipping it into its basic components, which I told you about yesterday, amino acids. So digestion has begun in full earnest in your stomach, right? Now, there's a regulation of gastric secretion in which the nervous system is involved. You think of food, so cephalic means head. That idea comes from the head. There's a gastric phase because there's pressure receptors in the wall of your stomach which feel the presence of food and start secreting something. And then there's an intestinal phase which tries to slow down stomach activity because once the food leaves the stomach, it's in a different compartment. Okay? Now, you know, even medical history is littered with sort of sayings like this. You know, sometimes when I go to mosque or when I go meet some of my friends who are very religious, they said, you know, so-and-so theologian, you know, St. Francis of Assisi said this so many years ago. And it's quite true, you know. Now, there must have been somebody who said, no acid, no ulcer. And it was by a man by the name of Schwartz in 1925. And unfortunately, it became an article of faith. Now, think about it. That acid in your stomach, I mean, it is potent. And so when people get sick and get ulcers, then everybody says, must be the acid, right? Now, so stress and lifestyle contributed to acid-induced gastric ulcers. That's what this man thought, Schwartz. And then so doctors said, well, if that's the case, if ulcers are being caused by acid, then we should neutralize the acid. And so the whole idea of antacids was born, anti-acid preparations, right? Now, that led further research, right? People took this to a huge extent, and they started making H2 receptor antagonists. Now, H2 stands for histamine. Now, when the head tells the stomach, get ready for food, right? One of the things that happens is gastrin, a hormone in your stomach wall, is activated. And that gastrin then activates histamine. Now, the cell that contains histamine has a receptor to it. So the gastrin has to bind to that receptor and activate the secretion of the histamine. People started blocking that receptor so that you won't secrete histamine. If you don't secrete histamine, you won't secrete acid, right? So it's a chain of events. Now, so people said, let's see what the chain of events are and let's block the secretion of acid. So H2 receptor antagonist, that means I'm going to block you so your histamine cell never gets to know that it has to produce histamine, right? And they took it even further. They made these drugs called PPIs, proton pump inhibitors. Proton means hydrogen ions. That's acidity. Those proton pump inhibitors were so specific. I think it was SmithKline and French, or one of these companies. And it became a $1 billion industry. You had ulcers, you get put onto a PPI, and the acid gets blocked. The acid gets blocked, and do you get cured? Well, we're coming to that. Okay. They found that once they withdrew the medication, the patient had a relapse. Okay. Now, the question people have been asking for a long time is why the stomach does not digest itself. And if you read there, it says the organ secretes a strong acid that can dissolve metals and kill living cells. How it avoids digesting itself and what happens when the safety mechanisms failed are explained. Now, this article was written in Scientific American in 1972, but they quote people going further back. So it was like the history of acid secretion. Okay? Now, Davenport said in this article, the organ secretes a strong acid that can dissolve metals and kill living cells. Gastric juice, as I told you, has this enzyme, which is a protein, pepsin, which can digest meat, right? Then why does this pepsin not turn against the wall of the stomach, which is meat, and digest it? And so why don't you, after every meal, walk around with a big hole in your stomach and bleed to death? That's a good question. Sometimes it does turn on its own against its walls, and you get ulcers. This man with an... where's my teacher? What's his name? Thank you. 18th century man of many sciences. So, if you get an article in Nature, your scientific career is sealed. I mean, you considered to be a world expert. This group, Ramakrishnan Bhaskar, I met him once. When I had met him, he had moved to Harvard by then, and I met him in Manchester. He wrote this article with a woman, a professor of medicine, Lynn Reed, who was at Harvard then, and it hit the cover of Nature. Why doesn't the stomach digest itself? So it's a perpetual question. So, why does the stomach behave as if it were made of porcelain? That was Claude Bernard in 1855. Is it because the apical tight junctions of the cells are different in the gastric mucosa? You remember those pictures I showed you of the epithelial lining of the stomach? Do they have something so special about them that they're totally resistant to this acid? That's a question. Or is it that the mucus on the mucosal surface of the epithelium affords this protection? Is that possible? So one horrible man by the name of Heatley said in 1999, mucus? No, it's only water. How is it going to protect against acid? It was very rude, I thought. But then there are people who said, let's look at the mucus. So they started opening stomachs and scraping the mucus off with a glass slide. And they found that Heatley was right. 95% of the mucus was water. But as I said to you yesterday, if you had two stomachs here, you take two glass slides, right? Or if you took one glass slide, you scraped the mucus, and you took the other glass slide and dipped it in water, the mucus would trail, but the water wouldn't. So if mucus is only water, then why is it so viscous? That's a question. Okay. Then it has some dialyzable salts. It also has proteins. It has nucleic acids. It has lipids. It has epithelial cells. It has bacteria, digested food, plasma proteins, digestive enzymes. Remember I told you yesterday, take a bite of the person next to you and you'll have all these components. So mucus is not only water, it's mainly water, but it's not only water. And it has a very special component, which only makes up about 1% of its composition, and that's a mucus glycoprotein. So it's a complex structure. It's a protein joined to a sugar, right? So it's a glycoprotein. It's a mucin or a mucus glycoprotein. And that is what gives mucus its gel-forming properties. So you see a layer of mucus right from the mouth, right through to the anus, and it sticks to those epithelial cells. And it protects them from all kinds of injury, and it hydrates those cells, keeps them hydrated. I need some hydration. Sure. Are you with me, ladies and gentlemen? We're just on slide 10 of about 200 slides, so just bear with me. Right. So now people started saying, this story about mucus just being water and having no role in protecting your stomach might not be true. This is how science works. So a new hypothesis, perhaps mucus has some role to play in the protection of epithelial surfaces. Let's revisit mucus. It has to be playing some role in mucosal protection, and that was in the mid-1970s. And the field of mucus biochemistry was born. So it's relatively new, okay? Now, then somebody asked a very interesting question. Hydrochloric acid, is it such a bad thing? If it was so bad, and if it was ulcer-causing, why did nature give it to us? It's potent, sure. It can burn a hole through your skin, but it must be performing some action in the stomach. Now, your food is always contaminated, no matter how sterile you think you make it, right? It always has something that the body will reject. Perhaps that acid was secreted, so in the stomach, your food really becomes sterile, right? So, suppression of acid secretion for too long a period can be problematic. You know why? I told you that there was a chain of events that led to acid secretion. If you suppress one link in that chain, you start going backwards and suppressing the other links. It's like you traveling on a highway, and suddenly you stop at a traffic light out there in Newlands, and then traffic starts building up and slowing down and stopping all the way back to Groote Hospital, right? So once you do that, then the body is going to think, we're not giving the stomach enough information, and it might just lead to messages to those cells to over-multiply, and you can cause a cancer. So that's another thing about acid. It's very important. Nature has given it to you for a purpose. Now, what is this mucus? The best way to explain mucus, glycoprotein or mucin, is that it has a bottle brush structure. The wire is the protein core, right? All those bristles are carbohydrate side chains. That's why it's a glycoprotein. That's the glyco part. That's the protein part. It's a glycoprotein. The ends form links with other ones identical to this. So this will be called a mucin monomer 1, right? Or a mucin subunit. Join it to another one like that by what we call in chemistry disulfide bonds, and you have a mucin dimer. Join it to another one, a mucin trimer. You join it to many, they all hold hands, a mucin polymer. It's the mucin polymeric form that's a gel forming one. When a mucin gets attacked, it's attacked there because there's no protection from these sugars, and gets attacked there, and monomers form. They can't form gels. These monomers fall into the lumen of the stomach. Mucus must fall. Okay. Now, this picture might not be very good, but it's one of those side chains, one bristle on that side chain. And look how many sugars it can have, up to 22 sugars. Okay. Now this, ladies and gentlemen, has become a minefield. People are looking at these chains, because if I took a scrape of any one of your mucus and purified these mucins out that I'm talking about, these molecules, right? One will not be the same as the other. It's never identical. That's one thing. So you can imagine the variation of mucins amongst you here, inter-individually. So it's very individual. The other thing is that in certain diseases like cancer, what happens is this chain doesn't form completely. It gets cut off. So there are new antigens. So sometimes you take a scrape of somebody's colon, you look at the mucin antigens and say, they're short. This person must be predisposed to something. He's not forming the full mucin molecule. Okay? So it's becoming diagnostically important. Now, so here's another diagram of the bottle brush, and I just wanted to show you that you join it to another bottle brush by disulfide bridges, right? And you can, in your stomach, when your pepsin turns against your stomach wall, it attacks the mucin that forms gels first. So this polymer is cut here and subunits are formed. You then get subunits that just fall into the lumen. You start thinning. If this happens too much, you start thinning the mucus layer that's lining your stomach, and it becomes less effective for protection. Okay? So there was this man who worked out, and his name was Adrian Allen, who worked out that 4 of those bottle brushes join to each other in a windmill conformation. If pepsin gets to them, the pepsin attacks it in what we call naked regions of the protein core, not in the part which is protected by sugars, and then you get monomers forming which fall into the lumen. So this became the famous windmill structure of Adrian Allen. Now, in disease, okay, how is mucus and gel forming mucins associated with disease? So I told you, you need that big structure, the polymer, to form the gel, and there's a dynamic balance on the epithelial surface. You've got a thin layer of mucus. If it gets attacked from the luminal side by pepsin, the wall starts to degrade, the mucus starts to degrade, but then the cells secrete more mucus to maintain that layer at about 100 microns. Very, very thin, but very effective. So it's a dynamic balance. Now sometimes you get overactivity of pepsin, or you get other factors which cause more degradation than synthesis. And what will happen? You'll have a weaker gel on your surface, and they think that that weaker gel, if the polymer is too little, then the pepsin will get to the surface epithelium and chew it, and you'll get an ulcer. Are you with me? Okay, so unlike ulcers, in cancer and cystic fibrosis, the polymer is in excess. It makes a gel that's too thick, and that could also be problematic. There was a man in Manchester, DV Park, who said, too much mucus or too little mucus is a dangerous thing. You just need the right amount of polymer in relation to the monomer. Okay, now, I told you yesterday about that long column in which you put in beads which are equivalent to marbles with holes in them. So we took mucus from somebody who was having surgery, or this group did, sorry, not me, surgery for something else, had nothing to do with the stomach, he had no gastric disease, and we put his mucus there, and it came off as a first peak because I told you the larger molecules move in between the beads and come out first. So if we took some chemical in the lab and took his mucus and broke it into monomers, then the mucus came out there, the mucins, right? So that is the mucin polymer, that is the subunit. Now look what happens in an ulcer. There's more subunit than polymer. Look here in cancer. There is a lot of polymer, but it's breaking down into subunit. So that means in ulcers and cancers, you can have weaker gels. Okay? So, this is the man, Windmill Allen. And I was part of his team at one time. I was young, so if you don't recognize me, that's me. And we had a great team. I mean, Linda Sellers eventually became Professor of Pharmacology at Cambridge. Right? That's David Hutton, whom I called Shit Hutton, and you know why. Andrea Leonard then eventually became a pediatrician, and he's working at the RVI in Newcastle. Julian Keogh became a very rich man. He joined Hoffmann La Roche in Switzerland as an advisor. He decided academia, there was no money. So he got his PhD and he moved on. And I came back to South Africa. Okay, and every Friday afternoon we had to go to see the boss. And when he had to sit and talk to you about what you've done during the week. And I think when he had to talk to me, he had to have a stiff drink first. The funny thing about him is he never drank Newcastle brown ale. He always drank something. And he said, when are you going to get me some wine from South Africa? So, his model for protection was this. You have the lining of the stomach, like I showed you. You have a layer of mucus on top of it. That's the layer of mucus. And also the cells secrete bicarb. So every time acid, which is hydrogen ions, come in, it gets neutralized by the bicarb. If the pepsin gets to the mucus layer, it only gets to the luminal surface and degrades the mucus there. The cells then secrete more mucus. This is kept constantly at 105 microns in your stomach, which is not thick, but it's there and it's protecting you. Okay? So you don't get ulcers. Now, sometimes this barrier can be overwhelmed. Okay? And so this mucus layer thins out. Okay, so here's a nice cartoon. there's the good mucus guys, they're producing mucus and bicarb, and here's the acid guys and the pepsin guys trying to attack the mucus layer, and this mucus and bicarb is being produced constantly to make sure that the protection is maintained. Okay? Now, when you always have this continuous layer, right through the stomach, right through the colon, right through to your anus. It stays there constantly. As I said, you degrade here, you get more produced here. But sometimes when this layer, mucus gel layer, is overwhelmed, then you're going to get bleeding, because you're going to get enzymes attacking, and you're going to get abrasion, you're going to get friction with food and fecal pellets moving through. So these cells start, this sort of, the integrity of this layer is compromised, your epithelial layer, and you start getting bleeding, right? So what happens is the mucus and the fibrin form a clot to afford further protection while healing is taking place. You call it re-epithelialization. That means cells come from the bottom to cover up the gap that was created in the formation of the ulcer. Are you with me? So the protection is still there. So now, as happens in science, Adrian Allen's windmill model was challenged by these two guys, John Sheehan and David Thornton. And they also had another Swede with them by the name of Ingemar Karlstedt. And these guys were big and threatening. And every time we met at an international conference, our group would sit at one corner of the pub, their group would sit there. They would send a PhD student out to pretend that he was going to buy beer to listen to what we were talking about. And I had collected some data in my studies that contradicted theirs. And I was terrified to have to meet them in Manchester and tell them that I was contradicting their data. And one night in Manchester, they were walking towards me. And I said, oh, now I had it. And it was John Sheehan and Ingemar Karlstedt. Dave Thornton was still much younger. And they walked up to me and they said, we heard you from South Africa. So I said, yes. So how's things there? You know, how's it going with apartheid and what's going on? Kind of thing. They started a conversation with me and they were perfectly friendly. By the time we got to talking about my data, they were more intrigued rather than condescending. And I found that when I went back to my group and told them, "Hell, they're hell of a nice guys," they said, "You're crazy. They're not nice at all." But anyway, they said the mucin polymer is not a windmill, it's just a straight chain. And it's far, far bigger than Adrian Allen said it was. But largely, the principle of protection was the same. The groups agreed on that. So it was unfortunate that the structure of the mucin still hasn't really been finalized or made. This is a picture I took with John Sheehan just before he died. This picture was taken at Cambridge 2 years ago, and apparently it's the last picture John ever took. By then he had been diagnosed with a brain tumor. And I was talking to him that night, and he said something very strange. He said, "You know, I'm glad I don't have Alzheimer's, because my father had Alzheimer's. I've just got a brain tumor, and they're treating it." But when I was leaving and I said goodbye to him and I said, "John, I'll see you," he said, "Do you think you will?" And I came back to South Africa and I heard that he had died. Very, very sad. He's actually given a hell of a lot to the mucus field. Okay. Now, I told you yesterday that the pig is very similar to the human inside. And I wrote this article in Gastroenterology, the pig as an ulcer model, long time ago. And this is the pig stomach inside. And as I told you that there was a procedure performed by Rosemary Hickman, Professor Rosemary Hickman, where they ligated the bile duct of the pig, and at 100% of the time, you got an ulcer in that area. And we could study this ulcer. And people came from all over the world, gastroenterologists. They wanted to see this model. They wanted to see the ulcer. How close is it to a human ulcer? When you treat it with the drugs you treat human ulcers with, does it make a difference? And I found that I could develop this ulcer in the spot, and after 16 hours, you start seeing the erosion. And by 24 hours, there's a blood clot, and the surface is completely wiped out. There's a fully formed ulcer in that model. And what I found also is that as the ulcer developed, the mucin polymer decreased in size. So my thesis then, and I think that was for my master's a long time ago, was that the thinner the mucus gets, the faster the ulcer develops. Okay? Now, so when people realized that mucus was playing a role, they said then, why should we keep treating with acid inhibitors? Because we need the acid. Why block the acid? Why block something that nature's given you? Why not enhance? Why not enhance the protective layer on the surface of the stomach? So we started using preparations like carbinoxolone, which is made from licorice, and put it on the ulcer base, and found that it had antipepsin activity. So it protected the surface of the stomach, but it had side effects. There was another one that was quite successful. It was called sucralfate, a viscous paste-like substance which adheres strongly to gastric mucosa at the base of the ulcer. And so it plays the role of mucus. It's a sticky substance, sucrose octasulfate. It has a lot of sulfate ions attached to it, and it sticks there while healing can take place. And then there was Denol, which is very popular, a bismuth compound, also binds protein at the base of the ulcer. So people started looking at preparations that would strengthen the protective barrier on the surface of the stomach rather than interfering with acid secretion. So all the above promote healing and do not interfere with the secretion of acid. And then Andre Robert came up with a new idea. He said, let's go the cytoprotection route. I heard Andre Robert in New Orleans in the 80s, and then he died not long after that. Yeah, I'm beginning to wonder, every time I meet somebody, the person dies. This is serious, very serious. Okay, so cytoprotection meaning strengthen the epithelial barrier by whatever means, okay? Strengthening the stomach surface epithelial cells. Now, gastric cytoprotection is protection against gastric mucosal injury by a mechanism other than the inhibition or neutralization of acid secretion. The enhancement of the stomach's own inherent mucosal defense mechanisms. It's a wonderful idea, okay? And one way to do it is to give people prostaglandins. Okay? Now, prostaglandins, one of its properties is to protect the mucosa of the stomach and intestine from becoming inflamed and necrotic when this mucosa is exposed to noxious agents. The property of prostaglandins is independent of gastric acid secretion and does not interfere with it at all. Okay? Now, it's very good, but why do you think it didn't last? Because you heard of prostaglandins given to women in labor, right, to actually promote birth because it causes muscle contractility. That became a problem, so we couldn't use it. It was lovely. It was lovely to use, right, for ulcers because it also stimulated mucus secretion, right? It tightened the gastric mucosal barrier. Okay? It improved the circulation of blood to the tissue. It was a wonderful idea, but it had bad side effects. Okay? Now, there was a time when lots of people with rheumatoid arthritis, older people, that were treated with NSAIDs. You've come across non-steroidal anti-inflammatories, right? And those worked very well for rheumatoid arthritis. People were free of pain, but they had bleeding of the stomach, especially if you had it without any food in your stomach, right? So that was the other thing. It's successful in one way and very harmful in the other. So as Lewis Thomas said, nature won't yield her secrets easily. So then somebody came along and said, you know what? Ulcers are caused by bacteria. Now, this was the first time bacteria were actually implicated in the formation of ulcers. This is Barry Marshall and Robin Warren, who won for that idea the Nobel Prize in Medicine in 2005. Now, their idea was, well, how you shouldn't treat ulcers with antacids, you shouldn't treat ulcers with all those mucus-enhancing compounds, give people antibiotics. They have an ulcer, give them antibiotics. They're both Australian, and they said it was caused by a germ called Helicobacter pylori. And if you look here very carefully, where the arrows are, those are colonies of Helicobacter in the stomach. We took those photographs in our lab. We published a paper in a Japanese journal because the Japanese are very interested in this, right? So this became the new idea in ulceration. Ladies and gentlemen, are you noticing how medicine and how science works? There's an idea, the scientists investigate it using the scientific method, and then they see a problem with it, and then they ask, it raises more questions, then they go on to the next thing. Do you see that? That's science, the beauty of science. Okay, so H. pylori became a big thing. Barry Marshall, to prove that those bacteria, Helicobacter, caused ulcers, he drank a broth. He gave himself an ulcer. He solved a medical mystery, but he could never treat his ulcer. He had it for years and years after that. The medical elite thought they knew what caused ulcers and stomach cancer, but they were wrong and did not want to hear the answer that was right. So Barry Marshall and Warren said that Helicobacter causes ulcers. So here's an example of a bacterium that is harmful rather than the bacterium we were talking about the other night. Okay? And so these were harmful and needed to be treated by antibiotics and cleared from the stomach and the duodenum. Okay? Now,
well, why didn't he do it for his own ulcer?
I think he drank too much of the stuff. Okay, so we wrote about the relationship of this Helicobacter Hale-Mani infection to the mucosal changes in abattoir and laboratory pig stomachs. We know that pigs ulcerate spontaneously. The slightest stress they feel, they ulcerate, and we looked for Helicobacter in their stomach and couldn't find it. An American group found it and said, this is what's causing the ulcers in the pigs. We couldn't find it. But we found that H. pylori binds to a mucin. H. pylori binds to a mucin, which is called MUC1. I explained yesterday that there are those secreted gel-forming mucins, like we've been talking about, and then there are those mucins that sit on the apical surface. Remember I spoke about breast cancer yesterday? Okay, so MUC1 is one of those. So MUC1 in gastric disease, that's Helicobacter pylori, and that Helicobacter causes gastritis first. And that eventually could lead to ulceration and eventually cancer. Now this is what Solly Marx said. Then why don't all the dogs in Cape Town get ulcers and cancer? Well, it turns out that there are different populations of this Helicobacter pylori. Some harmless and others more harmful. Okay? So we were fascinated that it bound MUC1 and it could even cause gastric cancer. Now, the cancer stomachs that we looked at here in Cape Town, most of them have Helicobacter in them. Okay? Now, the pattern of expression of MUC1 is altered in H. pylori gastritis. So when this germ causes gastritis, what happens is that MUC1, instead of going outside the cell, goes inside the cell. Okay? And it changes. It loses its sugar. It goes inside the cell and it tries to form, there's an inflammatory response to these germs, to H. pylori. It becomes processed and its sugars get cut off, and then it becomes upregulated, and that becomes again characteristic of the cancer cell, just like I told you in breast cancer. And in breast cancer, the cell becomes so overloaded with these MUCs, they start getting shed. And so they divert the surveillance of the immune system to the shed ones, while the cell can find its way and metastasize into other tissue. Okay? So, you have all these regulatory variations, and I'm not going to talk about splicing. So the MUG genes are upregulated and aberrantly expressed in inflammatory disease and cancer. So to what extent is this influenced by genetic differences? We don't know. But what we do know is when you compare a normal mucin to a cancer mucin, the cancer mucin has shorter sugar side chains, like I told you before. So this is becoming some kind of diagnostic marker, looking at people's mucin and saying, why are you secreting a mucin with short sugar bristles? Perhaps you're predisposed to something. Okay? Now, gastric cancer is prevalent in the Western Cape region, especially in the so-called Cape-colored males. It ranked at one time as the 4th highest in the world at 69.9 per 100,000, right? Now, are the mucins any different in these individuals? Well, we did a very detailed study in the gel I showed you yesterday. What I didn't tell you is these 2 large mucins were from normals and these 2 from cancer. The cancer mucin secreted this glycoprotein that at that time was unknown. And we were convinced that it was a fragment of mucin, that the mucin was being broken down and getting smaller and smaller and appearing as a fragment, okay? And this particular fragment, we called it the 55,000 factor, was prevalent it was not prevalent in donors. We got stomachs from organ donors, but it was prevalent in ulcers and was prevalent in various types of gastric cancer. The gastric cancer that you see in the Cape Town region, there's the diffuse type, the intestinal type, the poorly differentiated type, and the mixed type, right? The one that's called intestinal adenocarcinoma, that one, has a good prognosis. The others have a very bad prognosis, okay? Now, a student of mine then went on to try and find out and identify this protein. We had already published it in international journals as a fragment of mucin, but we had no evidence for that. We should never have done that. When he did his studies, and he won an international prize for the study, he identified this particular fragment not as mucin, but as another completely different glycoprotein, which was mixed with the mucin in gastric cancer patients in the stomach mucin. Okay, was this going to be our marker for pre-malignant disease? Could we go around to people in the Western Cape and say, your brother had cancer, there might be some problem with you, can we have some of your gastric juice, please? Can we put a tube down you and have some of your gastric juice and see whether you have this marker? We're actually working on it. It takes a long time, these things. I'll be dead and gone, somebody else will do it. So Tato Chirwa, one of my students, he did a PhD in my lab, won an international prize for it. It's called the Bunny Angon Prize, and he was able to travel to England and present his work there, which was very well received. Okay? And that's good night from the latest addition to our wider family. Thank you very much. I actually finished 3 minutes early.
Yeah, what's going on?
I'm getting old. Any questions?
Can I have you seen the film that was shown as well?
No, I didn't, but I heard that I don't have to give any more lectures because you know everything about microbiota in the gut.
If you like advertising, yes.
Yes. It comes down to about pH 1, which is an extremely high concentration, right? And if it gets any lower than that, the mucous barrier collapses. So you can have bleeding, very briefly, but as I said to you, the fibrin in the blood and the mucus then form an additionally strong barrier, and healing takes place very quickly. So it can go down to a very high concentration of hydrogen ions.
What do you think about the theory that if the stomach acid goes above 3, if the stomach acid is between 1 and 3, that is a feedback mechanism that tells the esophageal sphincter to close. So when you, and the reason why when the stomach acid is like at 4 or 5, it's still pretty potent.
Yeah.
And it's going to go, it can then reflux. And because the esophagus does not have the protection that the stomach has,
Yeah.
it feels like it's more acidic, but actually in fact it's not.
There's a lot of truth in that. I agree with you. I think the question is that there's a theory that at a particular pH, that sphincter that I showed you, you know the one where the esophagus enters the stomach, opens up and you get a reflux. Now, because you don't have the kind of protection you have in your stomach, right? So that acid can go into the esophagus and you feel very bad. You feel the heartburn. Sometimes people feel they're having a heart attack. Sometimes people who are having a heart attack think they have heartburn. That's the problem, okay? And I think there's a lot of truth to that. And I think that's the precursor, one of the causes of Barrett's esophagus, because if it happens all the time, it does.
In actual fact, I mean, my experience is that if you increase people's stomach acid, in fact, even give them stomach acid, you actually get a good response.
If you increase...
You actually give them stomach acid, or encourage the production of stomach acid.
Encourage the reduction, the production. But that's going to cause the esophagus to burn more.
No, it doesn't. No, it actually doesn't. That's my experience.
Oh, no, I don't know about that. No, thank you. I don't know, but I'll speak to some of the gastroenterologists. I don't know about that. I do know that if you neutralize the acid too much, you can be looking for trouble, because you're not going to get the microbes being killed. And, yeah.
In fact, isn't that, when you think about it, the H. pylori, which if the stomach acid was, if the stomach acid was at the correct pH, you said that it would actually cause the death of bacteria. And you also talked about how that Mach 1 yesterday was antibacterial. So, can you elaborate?
I'm glad you asked me that. What I didn't tell you is that the Helicobacter, even in a highly acidic stomach, actually finds a niche under the mucus layer, which is alkali. Oh, I'm so glad. I'm so glad you mentioned this. I've forgotten to tell you. So you have that layer of mucus on the surface of the stomach. And I said to you, it's not more than 105 microns, right? And I said to you that your acid can go down to pH 1. Now, can you believe this? Across that barrier of 105 microns, right? Just 105 microns, you can have a gradient from pH